speakers. We have two speakers enrolled for the talks, and I'm glad to introduce the first speaker, Moritz Reintjes.
Yeah, that's worst comes to worst, just the next speaker.
Okay, so the title of his talk is Constrained Conservation Laws, Geometric Theory. Moritz.
Yeah, thank you very much for the nice introduction. And well, thanks to the organizers for inviting me here. And also a special thanks to Dan Marchesin, because he proposed to me to work on these constrained conservation laws. And we had hundreds of discussions about that, and he helped me a lot with this project. So let me first give you a little summary of the talk. So that's what I mean by a constrained conservation law. So this thing, so we have a conservation law mapping the states to a lower dimensional space, so from Rm to Rn, and then the rest of the dimensions are filled with this algebraic constraint. So how does geometry come into the picture here? So if you solve the constraint, you get a manifold in general, so some curved space. And so if you just solve it, and then you restrict the conservation law to this manifold, you get a new conservation law, an n cross n conservation law, with the states now taking value in some manifold. Okay? And now the whole procedure here is to extend the framework of L.G.A and Glim for existence, for their existence theory, to this geometric framework. So you need to adapt some definitions and so on, and the proofs. Okay, and that's the subject of the talk, to extend the existence theory of L.G.A and Glim. Okay, so let me go through all the stuff now in more detail. So again, here is this constrained conservation law. So with this conservation law, with the accumulation of the flux function, can you actually always see this is okay, it's good, perfect. So the U as a state function sits in Rm. M is a larger space. G and F maps them to a lower dimensional space Rn, and constraint, just some algebraic function, fills up the remaining dimensions. Okay, and we assume that everything is smooth, so that we don't have to worry about that. Okay, and examples of these conservation laws are, for example, the Euler equations, with the equation of state being a constraint. I mean, extremely trivial constraint, but talking of the manifold, people might want to slap me in the face, but it is a constraint, and in multiphase flow, there are different examples, so let's see, sum of the saturations equal to 1 or so on. It's also a trivial constraint. Anyway, so yeah, and another feature of these constraint systems is that sometimes, I mean, quite often the constraint is not given explicitly, it's hidden, and then a feature of such systems is that you have less eigenvalues than equations. So whenever you see that, you might actually have some hidden constraints in your system. Okay, well, and of course for conservation of shock waves form, so you look at the Riemann problem, then from there you go to the Cauchy problem with Glim's method. Okay, so here's a way to solve such a system in theory. It's a very easy approach. So first of all, you solve the constraint, so you just invert the function c. So in more detail, I just mean that we want to find functions which go from Rn to Rm from some open set, such that this function takes values exactly in the constraint. So every point the function maps to sits in the constraint. So C of this stuff is 0. Okay? So that, and then you might need a couple of functions to hit the whole constraint, to fill the whole constraint. And then the collection of all these functions, that's actually what your manifold is. So to give you a simple example, here's a constraint. It's given by this formula. So the first component of u squared plus the second component squared minus 1 equals 0. It's just a circle, okay? And the solution is just such a function. So we map from this interval, we map the v to the sine and the cosine, so that parametrizes the whole circle. Okay, so that's then the manifold. Okay, so let me erase this stuff here again and go back to step 1. So back at step 1, we solve the constraint, plug it into the conservation law, so we get this n cross n system, restricted to the manifold of the constraint. And we go to step 2, we introduce a new variable. We take g as a new variable, so actually this g, of the omega. So this is again a function in Rn, and then we invert the f as a g and define this function, and we get a conservation law in standard form. It's an n cross n conservation law with a flux function, no accumulation function. That's standard form, and we can just go to step 3. We apply Lex and Glim existence theory, and we got existence, and everything's good, and the problem is solved. Well, of course, there's one little problem here, and that's a g, inverting the g. I mean, in theory, that's of course possible. You can assume that, but in practice, it can be really difficult to do that explicitly, or you might simply not like that, or whatever. So if you have problems inverting the g, then maybe this talk might be interesting for you. So why is the g, inverting the g, a problem? Because we need to introduce a new flux function for this change of variables to reduce the conservation law to standard form. Well, if you can't invert the g, we can't bring it to standard form, and we might get stuck there in explicit computations. So we took a different approach here, and we simply don't want to invert the g. We just keep the g, we don't change variables, and so we have no problems with that, so we can just continue. And now the procedure is to just keep the g, go through the whole thing. But if you keep the g, then your state space is a manifold. So you need to introduce this geometric setting, if you have a constraint, of course. Well, and that's what we do now. We go through the whole Lex and Glim's existence theory and extend the framework to such a geometric setting for an n cross n system of conservation laws with states sitting in some manifold. So like the circle, the surface of a sphere, whatever. So here's another example of a manifold, which I have a hand-drawn example. I'm not an artist, I'm sorry for that. So that's supposed to be a torus. So the manifold is the surface of a torus. So a torus is the surface of a bagel or a donut, whatever you prefer. So just picture the surface of, let's say, a donut. And the manifold has a feature that it's covered by these open sets. And so you can cover the whole thing by a lot of open sets. And to each of these open sets is assigned some mapping, which maps this open set on this abstract manifold down to Rn. And when you're back in Rn, it's all good and nice. You can do analysis, and that's what you want to do. So a manifold is just a space where you can do analysis. That's the whole thing. But the things are a little bit more complicated because you could have multiple mappings on the same domain or on the intersection of domains. So they can give you a different picture of your analysis. And the difficulties to make sure if you map in between these sets in Rn, that you get some consistent theory to map them. So that in geometry you say that the thing becomes covariant. So you want to introduce the right objects which transform in a nice way. So this gives rise to tensors because we want to do linear algebra in the end at each point. Okay, anyway, so that's a little review of manifolds. So let's talk about the Riemann problem. So, well, that's the Riemann problem. It's the same as always. We have this initial data with two constant states, and you have this jump at x equal to 0. But now these values are points on some manifold. Okay? Well, and here's the theorem we want to prove. So we assume the system is strictly hyperbolic. Its characteristic fields are genuinely nonlinear or linearly degenerate. And then if these two states in the manifold are sufficiently close, then you have the solution consisting of n plus 1 constant states in this manifold, separated by admissible shocks or reflection wave and contact discontinuities. And this is a unique solution within this class of solutions. So this probably looks very familiar, this theorem, because it's exactly Lex's theorem. It's exactly the same. The only difference now is we have to make sense of these words. So what's strictly hyperbolic in our setting? What's genuine nonlinear, and so on. So we need to define the right objects. And of course, we need to reduce to what we had earlier. Well, and in the first step is we want to get an eigenvalue problem. So we just pull out the derivatives here, and we get the derivatives of the g and the f. And that's exactly the same like in Rn, pretty much, except that these things are defined only in coordinates in exactly the same way. And in general, you should just think of them as linear mappings. So going from the tangent space of one manifold to the tangent space of another manifold. But that's good. Eigenvalue problems are connected to linear mapping, so that all makes sense. So we get this equation here now of these linear mappings. And let me just show you a picture of this differential of this dg and the df. So this is a manifold here, like part of a sphere, and the tangent space, that's just this linear space, this plane attached to each point. And this df and dg, those are linear mappings on this plane. They're defined on each point, and they map to another manifold, to the plane of another manifold in a linear way. So they're linear mappings, and we can talk of the eigenvalue problem. Okay? So that's a lot of talking. All I'm saying is that's a linear equation. We can associate this eigenvalue problem to it. Okay? So we have the eigenvalues Rk and the eigenvalues, and they depend on the states, so on the states in the manifold. So it's pretty much the same like before. It's just a slightly more different setup. Okay, now we can define what we mean by something being hyperbolic. So as in L.G.A.'s case, we just say the system is hyperbolic if we have n, so the n cross n system is hyperbolic if we have n eigenvalues and n associate eigenvectors at each point in M. And it's strictly hyperbolic if we have this ordering of the eigenvalues. So it's the same as before. But there's a little extension we can give to the notion of hyperbolicity here, which we get for free looking carefully at the proofs. And that's that this function g, in the standard setting, that's invertible. It's just the identity. Here it's some different matrix, some different linear mapping, and it can have a non-trivial null space. So it doesn't need to be invertible everywhere. This can break down on a finite union of hypersurfaces. So then you can connect the eigenvalues across these surfaces, and you don't get a problem there. And that's a funny feature of these generalized eigenvector problems, that you can have these structures and it all makes sense. So that's because here they just align directions, this eigenvalue problem. So the direction of these vectors must coincide, and the lambdas gives just some proportionality of the length of the vectors they map to. So the length of both vectors could go down to 0 on some hypersurface or some point, and this thing remains unchanged. So it could be constant even though the length of the images of the vectors changes. So that's a feature of these eigenvalue problems. Anyways, it's just a little thing, so let's not worry too much about it. And I'm actually not sure if there's any application in physics or engineering where this is important. Okay, now the next definition, genuine nonlinearity. That's the same as always. We just want the derivative of the eigenvalue along the case eigenvector to be non-zero. So we just choose to be positive. And this is just a notation to avoid the use of coordinates. I mean, this is really just the derivative in the case direction in the direction of the case eigenvalue. But you can actually find it in this invariant way, so you don't need to assign coordinates for this. But anyways, don't worry too much about it. It's really just a derivative. And here's one thing that's a little bit different. So if you look at Smoller's book, for example, he normalizes the eigenvalues by this condition, that this should be equal to 1, the derivative of the lambda. We don't do that here. We use the normalization from geometry, which is called parametrization with arc lengths of the curves, of the integral curves of these vectors. And that's a very nice feature because, I mean, it's the most natural parametrization in geometry to choose. And here it's very funny coincidence that this is exactly the parametrization that gives you the C2 contact of shock curves and rarefaction curves. That's a big surprise. So I was really surprised when I saw that. And this parametrization is also really important to prove some steps in Glim's theorem more rigorously. So for example, if you want to prove that the total variation is equivalent to the Glim function, so that those are in some sense equivalent norms. And this is a really useful parametrization to control the whole system. Anyway, so those are the basic notions. In linear degeneracy, it's kind of the same thing. The derivative in the direction of Rk should vanish. Okay. And then finally, weak solution. We need it for Glim's scheme, and it's just defined in the natural way. You just put in the g's and the f's here, and then for the initial data, you put in the g on the initial data. So this is your function for the initial data. And then you can use the divergence theorem again, and you see that those are the Rankine-Gonio condition in this setting. So you just get the g in here, so you can just, you just on Rn again, when you take the jump of the whole thing, so there's no difference here. Okay, so the proofs are all in this paper. So essentially, they follow the strategy of GLIM and then of LEGS. You just have to change in various places some things to make the whole thing covariant, so consistent with the geometry. And I tried to write this paper in a self-contained way. So there's also a little appendix giving you the background in differential geometry for page appendix, which you need to read this paper. So I think it should be possible to just read through it from the beginning to the end. Okay, so let me talk a little bit of the application to constraint conservation of this existence theory. So now we're back to the original system, the constraint system. And the assumption, the basic assumption is that the accumulation function ends constraint. So if you take the derivative on the state space, and we're in Rm, that this should be an invertible system. And you can lower this assumption on the dg again with our notion of hyperbolicity, but it's too annoying to write it down, so let's just forget about it. Okay, and with this assumption, and then assuming that this eigenvalue problem has n solutions and also n eigenvalues and eigenvectors, then you get the notion of hyperbolicity we want. We can apply our system, and we get this existence theory, so as a corollary. And what's also nice is you just need to look at two states in Rm, and if you see that both of them satisfy the constraints, then you know the solution exists. Okay? If you want to compute it explicitly, then of course you need to figure out how the constraint looks like. And if you think back to the beginning of the talk, this constraint, solving the constraint, I wrote it as C minus 1 of 0, so it looks like an inversion problem. But there's some good news. There's a way around inverting the C as well, so we don't have to compute the inverse of C explicitly necessarily. So there's a way around this, given by this theorem. So if you just compute the integral curves of these eigenvectors, so which give you the rarefaction curves, then this parametrizes the constraint. So you can start with the whole system. So where is it? This system. You just compute the eigenvalues, you get the eigenvectors. Then you just compute the integral curves in Rm, and they will just always sit in the constraint, and they parametrize a local neighborhood in this constraint. So that's just linear algebra, and you don't have to invert anything here, and then you know what the C is. Okay, and once you know the C is, then you can continue just working on that. You can introduce all your geometric objects by straightforward computations. There are computer programs that can do that for you. And you're good to go. You don't have to invert anything with this approach. Okay, so now we're already at the Cauchy problem, or Glimpse method. So what's the time actually is? It's like...
We used to have 10 minutes.
10 minutes, okay. All right, so again, with Glimpse method, we just have to start extending the objects Glim uses to this framework. And the first thing is the total variation. And this is pretty much the same thing. You just sum over partitions of the interval. And so we just restrict to t equal constant curves. So we are just an x here, so like for the initial data, for example. So that's the w is then just a curve in your manifold. So you just sum again over the partition of this interval. But now here you can't use the Euclidean distance on Rm or whatever. You need to use this canonical distance functions on manifolds. So that's just the infimum over all curves connecting these 2 points. So if you pick 2 points on your donut, then you look at all curves connecting these 2 points on the donut, and you take the smallest one and just integrate along this curve, taking into account the velocity of the curve. Okay, and that gives you the notion of distance on a manifold. And that's a proper distance function also. Okay, so equipped with this thing, we can also define the supremum's norm of a state. And obviously, we cannot just take, I mean, it's not even a norm anymore, so it's not a vector space where we work in. It's a manifold now, and we can't go to the tangent space here. So we just take supremum of this canonical distance function, and we have to put in some fixed state. So we start at some constant state, and then we look at the distance to this constant state of some curve we have. And that's, I call that d infinity of this stuff. But it's not really a norm because we're not in a vector space, so let's call it d infinity thing or whatever, d infinity guy. Okay, so now having these two things, we can look at the Cauchy problem. So again, we have this n cross n conservation law, initial data, so that's just a curve in your manifold. And then you have the assumption of strict hyperbolicity, genuine linearity, and so on. And you assume that you have small initial data. So TV of the initial data and the d infinity guy of the initial data is small. So the initial data must be in a small neighborhood around this constant state. So it's a local problem in this sense. Okay, and then we have the existence result of Glims. So it's the same statement. We get the bounds on the d infinity guy and the TV guy of the solutions in terms of the initial data. And we get this Lipschitz dependence, this L1 Lipschitz dependence, so the bounds with the initial data. Okay, so it's the same theorem. Okay, here's just to remind you of the weak formulation. Okay, and just some remarks on the proof. So luckily, some of the steps, so whenever you work in the parameter space and look at the wave strength as a measure of something, so the estimates on the Glim function, also probably the hardest part at least from an analytical point of view, you get that for free. You can use the proof word by word. It's exactly the same because you work in the parameter space of the curves, of the shock curves and refraction curves and so on. And the parameters don't care where your curves sit in. If they sit in Rn or in a manifold, it doesn't matter for them. So you can just take that and get it for free. And then there's some other things we have to put more work in, and then the whole convergence issue, because we have to change the norm to this d infinity guy and so on. So that's a bit different, so you have to put more work in there. But again, you also get that you also use Haley's theorem, you have to extend that to this framework. And then you just go through the whole setting and you get again this existence result. Okay, well, since there's still some time left, let me just show you a little bit how the proofs look like. So this is the proof for the C2 contact of shock and rarefaction curves. So here you differentiate the Hugoniot locus and so on, and then you differentiate it again. But as soon as you take second derivatives, things become complicated because you differentiate vector fields, and then you need covariant derivatives. So covariant derivative, it's just a derivative, but if you just take a derivative, your vector might run out of the manifold, and you always want to push it back into the manifold. So you need to throw in these perturbation functions, these Christoffel symbols, that push your vector from the second derivatives back into the manifold to be tangent to it, and you have to smuggle them into these equations. And of course, if you do that, this could go wrong. I mean, the equations must have the structure that allow for that. And luckily, whenever we run into these problems, there's always some combination that you can just put it in here, and you also have to put it in at a different place. And these things just combine perfectly to give you the covariant derivatives and to make the whole thing geometrically consistent and covariant. So it's a very nice feature of this method. So I was, when I worked it out, I was always afraid that it will just break down now for such a stupid thing like a little computation like this. But it all works out. Okay, and then it's just the use of the arc lengths again. So let's just skip that and come to the conclusion. So if you don't like to invert the G, then maybe you should look at geometry here. And then it's this paper. Maybe you should just read through the paper if you're stuck with the G. And also, beyond the problem of inverting the G, if you take a slightly more geometric approach, then maybe you also get a new perspective on a hard analytical problem. So you might get nice ideas to simplify the problem by looking at the constraint and finding a nice simple geometry for the constraint. And this might be very fruitful if you get a new perspective, a new tool. Maybe this is worth looking into. Okay, so that's all. Thank you for your attention.
So the section is now open for questions.